Huh? That's the camera. They put this as the camera? Yeah. This is not being shared. The screen is showing the camera. This will show the view. This is the view you're getting. No, we don't want this. Just remove it. The mic will move this one. But mic, you had a separate mic. No, they just set it this up. This is the camera. No, we don't want this camera, right?
No, we want to cover it by this camera.
No, we don't. We are covering the screen as it is.
So if she's writing on the board, then she's
not going to write that much on the board. Right?
I would be writing a lot.
Because this doesn't show up. That's why we had set it. That's why we had set it like that.
What side do we want? Do you want to move this?
You can keep both. If she has to write.
Okay, let me see what to do. Okay. Anyway, so welcome everybody to today's seminar colloquium by Bhumika Mittal. We are very proud of her because she's a first-year undergrad and she says that she's not a mathematician, but you guys can decide.
Thank you for the introduction, Professor. Welcome everyone. So today we are going to talk about the existence of balanced Lagrange sequences. I wrote this paper with Professor Matthew Baker, Haran Molly, and Eric Teng. They are good friends of mine. So before we get into the math part, let me show you a magic trick. So any volunteers for the trick? So here I have a new deck of cards, which these are 52 cards plus 2 jokers, that is 54 cards. And I have my volunteer here. How many times do you want to cut this? 3. Okay. 1, 2, 3. You can see this is a very random ordered card. I'm not ordered them. Okay, so now I'm dealing with the first 5 cards, or do you want to cut them from the middle? It's fine. It's fine. Okay. Can you pick them up and see? Don't show to me. Now the possibility is that you must be having cards of 2 colors. Discard the cards which have minority color. Amazing. So now if you have discarded the red cards, you must be having the black cards with spades and clubs left. And if you have discarded the black, you must be having black hearts and diamonds. Choose any one of the suit which you like and discard the other one. Okay, so now you have 2 cards left. Let's choose any one. And try to send me the image of this card. Like just look at it and try to send me the image of this card. Okay, so my claim is I don't know the color of this card. I don't know the suit of this card, but I can identify which card it is. But before I do that, let us try getting the math how I can do that. So this order, though it looked random, wasn't random at all. It was predetermined. And from the order and the position of the discard, I can uniquely figure out the 5-hand substring of this 54 string. This particular deck, which the cards were arranged in, is called a sledgehammer stack. You can see the stack on the screen here. So here S represents spades, C represents clubs, H represents heart, and D represents diamond. So if I convert S and C into 1 and H and D into 0, it will become a binary string of red and black, where red represents 0, black represents 1. And this binary string is known as De Bruijn sequence. So now what are De Bruijn sequences?
What about the G's?
I will deal with as an edge case later. So what are binary De Bruijn sequences? So binary De Bruijn sequence of order L is a length 2L binary string where substring of length L occurs exactly once. So let me give you an example for skew L. let's say I have L equal to 1. So my 2L would be 2 to the power 1, which is 2. So one of the simplest example would be 0, 1. Here 0 occurs exactly once and 1 occurs exactly once. Let's take L equal to 2. So my 2 to the power 2 is 4. The sequence would be 0, 0, 1, 1. That is 0, 0, 1, 1. Here 0, 0 occurs exactly once. 0, 1 occurs exactly once. 1, 1 occurs exactly once. And since I've drawn it as a cycle, you can see the cyclic sequence. So 1, 0 occurs exactly once. Now, if I define it as a generalized sequence, I can say this 2L, which is 4, as an N. L, which is the length of the substring, I'll keep it as an L only. And this is occurring exactly once or at most once, I'll call it as my K. So when we have equal number of zeros and ones, I call it a balanced de Bruijn sequence. Moving ahead with balanced cyclic de Bruijn sequence, generalized one, I have 3 parameters: N, which is the length of the string, L, which is the length of the substring I'm dealing with, and K is basically the length. At most time, the substring of length L occurs in my sequence. So for a definition's sake, a balanced cyclic de Bruijn sequence with parameter N, L, K is an n-bit binary sequence that satisfies the following properties. That the sequence contains equal number of zeros and ones, which makes it a balanced sequence, and each substring of length L occurs at most 1k times. Next, to find such sequences, because for the magic trick, this was just one possible sequence, but you might need another sequence to make a variations of the tricks. We'll try to find out more such sequences. So to find these sequences, we came up with this theorem which says that for any positive integer n, l, k, a balanced cyclic de Bruijn sequence with parameters n, l, k exists if and only if n is even and k is greater than or equal to n upon 2 to the power n. Now I'll prove this theorem, but before proving this theorem, we need to do some homework. We go through some lemmas, definitions for de Bruijn sequences, and in the end, we'll prove this using induction. So let's go through some important lemmas and definitions. So first definition I have is de Bruijn graph. So what's a de Bruijn graph? A de Bruijn graph of order L, I'll denote it as GL throughout my talk, is a directed graph. A graph is basically a set of edges and vertices. And if I talk about directed graph, it basically has a direction. So let's say these are two vertices, V and W. If I draw a line between these, that's an edge, E. So right now this is an undirected graph, so I can just write it as VW or WV. But if I give it a direction, this will become an ordered pair, VW. Now I cannot represent it by this. That would be wrong. That's a directed graph. So a de Bruijn graph is a directed graph on 2 to the power L minus 1 vertices, which is labeled in a particular order, that is 0, 1 L minus 1 and 2 to the power L edges. So let's do some lemmas. First of the lemma is every vertex in the de Bruijn graph has in degree and out degree of 2. So to quickly explain what is in degree and what is an out degree. Let's say I have this graph with 3 vertices, A, B, and C. I give it this direction. Okay. So for the vertex A, there are 2 edges which are going out of it. So it is in degree of 2, but it has no edges that is coming in it. So it has out degree of 0. For C, it has.
I think it's the other way around. Other way. Out degree is 2, in degree is 0.
Yeah, out degree is 2, in degree is 0. For C, we have 2 edges coming towards it. So it has in degree of 2 and out degree of 0 because there is no edge going out of it. For B, it has 1 in degree and in degree, out degree is also 1. So the claim is of every vertex in a de Bruijn graph has in degree and out degree of 2. The first one is the graph for L equal to 1, that is 0, 1. You can see that there are 2 edges coming out of it and 1 edge. Like for 0, there are 2 edges coming out of it and 2 edges going in it. So if you intuitively see, this works for all the L. Moving to the next lemma, I said the Bruijn graph is Eulerian. So Eulerian graph is a connected.
What is a De Bruijn graph?
Sure. So basically, a De Bruijn graph of order L is a directed graph on 2L vertices and 2L edges. Did I answer your question? Yes, sure. I'll show it demonstrate to the edge. So here, I take 0, 1, 1, 1, 1, 0, and 0, 0 as my vertices. That is the substring I'm taking. The one I took here, 0, 0, 0, 1. And I connect them as like, so it's a cyclic sequence, right? So 0, 0 goes to 0, 1. And I name it as 0, 0, 1 because here I have 0, 0 and 0, 1. So the naming convention for this would be 0, 1 because from this string I can get both 0, 1 and 1, 1. And similarly, this goes on. Did I answer your question? Yeah, so the Bruijn graph is Eulerian. So Eulerian graph is basically a connected graph which starts and ends at the same point and goes through all the edges once. So it's a well-known theorem that for an Eulerian graph, the vertex should have a even degree and the graph should be connected. From the previous lemma, you can see I showed that in degree and out degree are equal. So that suppose it's m. Here we know it's 2, but suppose even if it was m, we know that it's an even thing because it's 2m. So it is sufficient to show that GL is connected. So let us assume any vertex V and a second vertex V dash represented on the screen for this GL. These are generalized vertex. So I can show that there exists a walk from V to V dash, which is this following walk. Moving towards the next lemma. Just to simplify this, there is this simple definition that for the graph, if the last bit ends with 0, I color the edge as red, and if it ends with 1, I color the edge as blue. And it is balanced if we have equal red and blue. So for any vertex V in this graph, V has one red and one blue out edge and an in edge of V are of same color. How do we prove this? So for any generalized vertex in GL, by definition, we know that out edge would end with one of them would end with 0 and one of them would end with 1. So that's one red and one blue. And again, from the definition, we know that any in edge would end with the same bit. So that from definition would be same color. It could be either red or blue. Moving to next lemma. A balanced circuit of length n in GL corresponds, that's a 1-to-1 correspondence to a balanced cyclic De Bruijn sequence with parameters n, L, and 1. That is, L in the graph of n bit, the substring of L occurs exactly once. So let's take an edge of the circuit L length n, which is denoted by this. So this is a circuit where each edge of length n. So the L bit substring of length n in this sequence is precisely the correspondence to the edge of the circuit length n is this. B0, B1 to the BL minus 1. Then we go to B1, B2 to the BL. And similarly, we go to Bn, B0 to BL minus 2, which becomes the circuit. Thus, as the edges on a circuit are distinct, so are the L bit substring. Here you can see this again. And we know since the De Bruijn sequence, balanced De Bruijn sequence, the number of zeros and 1 are equal, and hence the lemma follows. Moving towards the next lemma. If the graph GN has a balanced circuit of length n, then the graph GL plus 1 has a balanced cycle of length n. This follows from the, I won't prove it right now, but this follows from the fact that GL has a balance, the vertices of GL and the edges of GL plus 1 has a natural bijection.
Do you want to say that GL is contained in GL plus?
Yeah, that's an intuitive proof, but we can prove it precisely, saying that the GL has a vertices which has one natural bijection to GL plus 1. But yeah, that's a very intuitive way to think about it.
And cycle and circuit means the same.
No, so basically a circuit goes through each vertex, whereas cycle is a type of a circuit where each edge is visited once. So in circuit, you can have like a multiple visits of an edge, but in a cycle, it's exactly once.
Cycle is the auxiliary part.
Kind of.
So then it's just left out.
Sorry?
In circuits, will there be a just left out?
Possibly. Another lemma, that length for, if we have L equal to and greater than 2 and N be an even positive integer at most 2 to the power L, then the graph GL contains a balanced circuit of length N. This can be done by induction on the L, which again due to time constraint, I'll move ahead and come to our original theorem. So the theorem was that for a balanced cyclic de Bruijn sequence with parameters N, L, and K, it exists if and only if N is even and K satisfies this condition that K is greater than equal to N to the power N upon 2 to the power L. So for the one direction, I prove it saying that since the balanced de Bruijn sequence has an equal number of zeros and ones, N must be even. Moreover, by pigeonhole principle, I can see that K is greater than equal to N to the power N upon 2 to the power L, since there are only 2 to the power possible at-built substrings. Now, the main part is to show that these constraints are sufficient for a balanced cyclic de Bruijn sequence to exist. So I'll assume that K is the ceiling function of N upon 2 to the power L. And then using induction, the base case follows from the previous lemmas, which we did here. So now let's assume that this is true for K, and we'll prove it that it is also holds for K plus 1. So for any balanced cyclic de Bruijn sequence with parameters N and we'll take two balanced cyclic de Bruijn sequences, one with parameters N, L, and K, another which has edges as B dash, B0 dash, B dash 1, B dash 2, L minus 1. So the parameters are 2L, L, and 1. So now if I think about it like this, if I merge these two strings here, the length of the sequence would be N plus 2L. The substring would be L, and each substring occurs exactly K, at most K plus 1 times. So this thing holds for K plus 1 as well. So from induction, we can say that since it holds for K plus 1 and we assume it's true for K, our theorem follows. A theorem is valid. So now let's go back to the trick.
Hang on. Can you illustrate your two fields from these examples, or these are too small?
I think these are too small, and to do it for 52.5, it would.
I mean, just with these examples, can you show what the lemmas do?
Sure. Each lemma you want to go through?
Yeah, just lost in your.
Oh, this one. This one.
No, so I just want by example what it means. Because there's some confusion.
So I do have an example. So can I go through this later and complete it all? So yeah, for our trick, as I mentioned, the joker part. So since there was a joker, I cannot classify it as either 0 or 1. So I would want to remove the joker and make my trick more efficient. And thus this theorem. So if I just pick up the joker and remove it, basically my stack breaks down because the joker was affecting the 10 substrings. So to make my trick more efficient, what we did was we tried finding the de Bruijn sequence for on 52 of length 52 with same parameters where L is 5 and it occurs at most 2 times. So this is one of the example we found. And if we use a random generator and write a code for the same, this is the cheat sheet a magician will use and see the discard orders of the cards to find out the order and the position and fill figure out which card was in the end held by the volunteer. So,
Remember that.
sorry, what?
One has to remember that.
So there are two ways to do it. If you're a very proficient mathematician with a great memory, you can remember this, or you can make a website out of it and just feed in the numbers and get.
You are saying random ordering of the tasks that were there assigned to zero. So random permutation of the 52 cards. So writing code for the former is, writing code for the later is very, very
so this string, basically we get the string and we verify this is a balanced Bruijn sequence, and then we basically assign the suits, and from the suit we don't even need to assign the number. If we have a proper sledgehammer stack with 52, we can assign a random numbers to it. So say first is heart, so I just assign it A7 3 like that.
I think Professor is trying to say, is it like just a random permutation or is it like spatially ordered?
It's random.
No. So I think the assignment is whichever card is in the assignment. The assignment would not be random series, right? Based on the pattern which you are arranging this.
So the specific thing is this.
Back here, this characteristic of design would define for you what exactly is the pattern.
Yeah, so 0 0 says that
0 0 0 0, the 5 zeros, right?
yeah, so first 5 right cards.
Yeah, they would say that first 5 cards would have to be red.
Yeah, and then
on the parameters, then the next 3 cards will have to be black. Then
yeah,
again a red and like
yeah,
that.
exactly. We find out that. And
So
the
it is something which is decided by the sequence.
the random part is assigning A 7 3 Q 2. Suit is also not random. It is done by the program. I don't have a program for it, so I'm not sure how to do that. But
yeah, so I mean, I think random is being used in a non-technical term that you have a stack of cards. Whatever its thing is, as long as you put the colors and you map them to the Bruijn sequence, the trick might work. The trick will.
It should be possible. I mean, so I had done something, but over there, you can just go back. So here, every card would be associated with a string of 5 binaries, right?
yeah.
So you can use the first 2 for defining the color and the whatever suit it is, and then the next 3 can tell you what exactly is going to be the card's value.
Exactly. So I decide card discarded.
Yeah.
So I observe that. And if I remember the cheat sheet or have a cheat sheet handy, I know which binary string it could, which substring it could be. And then from the substring, I know that these are possibly 2 or 3 substrings it would be. From the next discard, which is the suit discards, I know that one of the suit is discarded. So the other left suit, I know that there are these 2 possible cards. Now, since I kind of identified all the 5 cards, from the index, I can just say that since they are holding, let's say, index 3 card. So I know which is the third card. Or just to be more impressive or just to be more presentable, you can actually reveal all the 5 cards.
Initial stack is not random, but his operation.
No, I was just thinking that here the first few digits are 0 0 0. So if 0 represents red, and again a 0 is a heart.
Yeah.
Then the next 3 zeros would represent an ace, because like 0 0 0 is A. Like the binary representation minus 1 sort, plus 1 sort.
Not sure if I got your question.
No, that won't work, right? How would that work?
That might not work here because she
Because
has
you don't
got
have,
2
I mean,
cards.
they're cyclic, right? So you have to use the next, for the next card, you have to use the next 5 digits. Then,
Can you just show the next one?
so if you can do an example, I think it might clarify. Start with the lemmas, with this example.
Professor, I'm not sure if I have an example at top of my head.
This thing, what is the graph, for example? For
This one?
Yeah.
What are this is an axis?
Sure.
So just connect and explain how it works. So 0011, how you get the graph.
So since we have what this is 0 0 0 1, we connect it in one of the direction because this is the direction it is working. 0 0 0 1.
Yeah.
Then similarly, this happens for 0 1 1 1 1 0 and 0 0.
Why
That's
is it already?
because it's a connected graph. and each vertex has an even degree. So that's a kind of a well-known theorem in graph theory that if each vertex has a
fine. So why each one even degree? One is coming in and one is going out.
yeah, 2 is coming in, 2 is going out. So basically degree is 4.
Why 2 coming in? Huh? Why? So 001 is coming to 01.
Yeah,
Then why 101 coming?
that's an edge name 1 0.
Because it could be, yeah, I got it. Okay, so we just putting 1 bit here. So okay, fine. So that's okay. Next line. Eulerian is fine. It is connected and it's.
This is just a way of assigning the things, definitions.
Balance means in the example, balance means what?
So suppose this one, we have this edge which ends with 0. So I put it as red color, and this which ends with 1, I put it as black color or blue color. So I have red and blue. So if I have equal number of red and blue edges, it's a balance.
Okay, fantastic. So next level. That's what I meant. Okay, this is the definition now.
So now from the definition of an out degree, the last bit, one of them would be 0 and one of them would be 1. So that would be 1 red and 1 blue. And from degree, since it's originating from the same vertex, the last bit would be same. So then one of, like, it would be of same color, it could be red or it could be blue.
So this thing is illustrated by this.
I'm not sure if I have an example for this at the top of my head. I can come back to you on this later.
Okay, so if you have a different sequence, then you can make
A one-to-one correspondence with another De Bruijn sequence, which is of length L, and substring is of length L, and each substring occurs exactly once in the sequence.
okay, yeah, that makes sense.
So I had a question. If you go to your final trick. So in this one, there are some 5 tuples which occur twice.
Yeah, at most twice.
At most.
Correct.
So how would you be able to differentiate between the two? As in, it could have been the beginning 0000 or that middle 0000.
Yeah, so that's why we discard the suits, and from the discardment of the suit.
So if you're discarding the suit as well, then that would mean that you're asking for more information than just a binary.
No, I just asked them to discard any of the suits.
So first is the discarding of the colors.
Yeah,
So
first
if
is
you're discarding one color, you already have made one binary choice.
yeah.
So now if you ask them to discard a suit, you're making another binary choice,
Correct.
which would be more than what this information produces.
So suppose for this stack,
Yeah.
for the first is like the 5 red cards,
Yes.
and if they discard, so they don't have the black card to discard, they just have 5
So
red
what I'm
cards.
saying is that this is not a binary, this is a quaternion.
But a sequence is binary. And from the binary, the assignment of the suit is basically a different thing, which is how basically scope of implementation.
So can you do an example from this only? Let's I've discarded 2 reds, and then I've discarded 3 reds, and I've got 2 blacks. So I have discarded position 1, 2, and 5. So
Let's
you're
say,
observing that.
okay, so
So
let's
there's
say
a
I have
middle
this
of-
sequence, this string,
Yeah.
which is 3 of hearts, Q of hearts, A of clubs,
So
and
this
4
is
of diamonds.
one possibility. Is there another possibility now?
Okay, this is 0 0 1 1 0.
And it
Let's
could be
find
1
it.
1 0 0 1 also.
Correct. Let's find out the other possibilities for this. 0 0 1 1 0.
Does it have to be one with with 3 zeros and can
I'm sorry, I didn't get your question.
you have to have those two sequences?
It's not necessary. It could be at most.
It could be
Yeah. So probably this is a unique sequence which we chose, but there would be sequences which have 0, 0, 0.
Next step, what does not do? I remove one card.
So you remove one color.
So I remove one color for the first step. So I remove 3 cards, 4 cards, and 4 of them.
So I'm now observing the index. So you remove the index 0, you remove the index 1, and you remove the index 4.
Yeah.
So you are remove 0, 1, 4.
Right. And so now I have got ace and 4 of clubs.
Yeah. So you have index 3 and index 2 and 3 left.
I throw away ace.
You do not throw away anything in the second because you're not removing any suit. You have same suit.
Okay.
So that's also a thing that you haven't removed any suits. It's of the same suit. And now I kind of have an assumption that which string you have.
So I have either ace of clubs or 2, and then I pick one of them.
Yeah. And now if you pick the second index card, I know that you picked ace of clubs. Or if you pick this third index card, I know that you picked ace, 2 of ace.
The only issue is that final k or whatever you had, if this was less than equal to k, so there could be k possibilities.
At most k possible.
At most k.
Yes. Do we have any other questions? Thank you.
Any further questions or comments?
Right. This probably can be carried for instead of binary to possible. Just taking that say D. But I mean D many of options.
I'm sorry. I don't.
Yeah, you are talking about the binary sequence.
Correct.
Instead of that, you could consider sequence which takes value within, let's say, D many options.
Like 0, 1, 2, right, trinary sequence of that. Okay. So we haven't thought about it, but there was a place where we left it as a further scope of study. Because that could be considered, but since it's based on a card trick, we have just 2 colors, so that's why we were going through that.
So what were you explaining about the jokers?
So what happens when we have a joker? Suppose there's this case where you get 2 red cards, 2 black cards, and 1 joker. And when I say that remove the card of the majority color, my audience would be confused because they don't have a majority color. So from that, a magician can say, okay, I think you have a joker, just remove the joker first and then remove any 1 card. So this kind of is an edge case for my trick. This won't happen always, but this might happen in certain cases. So this kind of makes my trick confusing, or maybe at times it fails because I need to do a second guess. So to make this trick more efficient, I want to remove the joker from the entire stack and find out a sledgehammer stack for 52 instead of 54. So basically that first deck was given to us by Professor Matthew Baker, who represented this problem to us. And we wanted to make this trick more efficient. That's why we plunged into the De Bruijn sequences, find out that if we can have such a balanced De Bruijn sequence. And from that, we just got the balanced De Bruijn sequence of length 52. And after we got that, we just assigned the suit to it and then a number to it. Now my sequence do not have a joker. So I can easily assign 0, 1 to it, or I can easily do a trick where there would be no confusion because out of 5 cards, 1 would be in majority, 1 would be in minority. And if I just simply pick out the joker, my trick will fail because there would be substrings. It will affect 10 substrings if I just simply pick out the joker from the middle of the stack and remove it. So for 2 substring, I think there would be the same order and position of the discard. So I cannot guess which substring it is, and basically the trick fails at that point.
Substring should be outside.
And not necessarily, you can try doing it for the different substrings. Actually, we were doing that for the 3, I think, and a non-joker stack with card 5 as well. So, but that's basically in the progress.
If there are no further questions,
Thank you.